have a container of gas, say hydrogen gas, and pour energy into it, for example by heating it up or running electricity through it, it glows different colors. But the colors the gas glows are surprising. As opposed to a normal light bulb, the gas doesn't glow in all the colors of the rainbow. The gas emits specific colors. This is called a discrete or non-continuous emission spectrum. Each color of light has a specific wavelength, and each wavelength has a specific energy. The lower the wavelength, the wavier the light is, meaning it has a higher energy. The exact formula is E equals hc over lambda. Here, E is the energy, h is Planck's constant, c is the speed of light, and lambda is the wavelength. Since putting energy into the gas produces a discrete emission spectrum, there must be something discrete about the energy of the atoms that make up the gas. If our goal is to create a mathematical model of an atom, then reality requires the model to have discrete energies. Also, other experiments have shown the following. There must be a positively charged nucleus and negatively charged electrons somewhere in the atom. Another observation that were perplexing scientists at that time is that atoms are very large compared to the small size of the nucleus. These are nature's requirements for our model. The simplest model that fulfills these requirements is the Bohr model of the atom, named after its creator, Niels Bohr. In Bohr's model, electrons orbit a nucleus composed of protons and neutrons, similar to planets orbiting a star. So the atom is very large compared to the nucleus, which is what we expect. Bohr also restricted the electrons to orbit only at specific radii. The reason isn't immediately obvious. Electrons are charged particles, and physicists already knew that charged particles radiate energy when they accelerate. This means that if electrons are free to move further or closer to an atomic nucleus, they would radiate energy as they moved around the nucleus, falling towards it. So Bohr's solution was to simply restrict electrons to specific orbitals, each with a specific radius. These are also called stationary states. The emission spectrum, which is the possible energies of emitted light of an atom, comes from the different jumps in energy that the electron can make from a larger radius to a lower radius. This is where the discrete emission spectrum comes from. Though these theoretical predictions of energies are very close to reality, this model has some issues. Firstly, it only works well for hydrogenic atoms, which are hydrogen-like atoms with only one electron. Secondly, the Bohr model predicts specific, exact radii and positions for electrons. The radius associated with the ground state of hydrogen is called the Bohr radius. But when we actually measure the radius of an orbiting electron in hydrogen, we don't get a specific value. Instead, we get a probability distribution across all space, kind of like a cloud. And the average of the distribution is at the Bohr radius, which means the electron has a chance of being found anywhere in space, with the average at the Bohr radius. Physicists were also observing matter behaving like waves, and the Bohr model fails to explain this phenomenon as well. So, for this new model of the atom, nature's requirements are discrete energy states like before, that doesn't change. Position and possibly other values are modeled by a probability distribution, and matter has to have wave-like behavior. The model that fulfills these requirements is called the Schrödinger model. In the Schrödinger model, each state of the atom is described by a wave function. This wave function describes matter as being wave-like. Any state of the electron can be described by a wave function, and each wave function has a specific energy. The wave function's energies, however, are subject to certain constraints, making them discrete. This is exactly what we want from a model based on reality. Finally, the spread of the wave function across space describes a probability distribution for the position of the electron. But still, this model fails to describe certain phenomena. For example, it cannot describe relativistic particles. For that, we need a different model. Also, though it can deal with hydrogen atoms perfectly, there is no need to use it if a simpler, easier to use model like the Bohr model can do the same job, with the same accuracy, and faster. We can always use a technically less correct model, instead of using a more complex model, if it will do a certain job just as well. Thank you for watching.